Okay, good morning, everyone. So I think we now continue our class. Um, Last time um, we have discussed about the strain, the small displacement, or the small strain behavior, which is very common problem or common phenomenon in structure, in structure. And then I'm adding some additional notes on thermal strain. So strain that is because of the temperature, okay, because of the difference of the temperature, whether it's increase or decrease, and there will be a slightly strain because of this temperature differences. And then today I will talk about, at the beginning I will talk about this, which we discussed a little bit. So this is a tensile specimen for tensile testing in mechanical testing. So basically this is, I think, every major for material science, every students in that major, they are going to work with this at the beginning as a principle, because this is where they are going to get the very basic mechanical property or material property that we can have and develop from this testing. Okay, so from tensile testing you will get, I think, most of the mechanical property right from the data set. So if you have seen or you have worked with data sheet for tensile testing, you will get the the strain or displacement. Okay. So from here you will get the data you will get from this machine or the equipment is, first you will get the displacement, and then force. So you will get D and F. Okay. So we need to work with this data, and then we need to take some formulations. And I think when I was still student, I also got to do this experiment. I don't know whether have you experimented with this? Tensile test, ready? Right. So you get, I think, different equipment will have different setup, but usually you will get the displacement and force. And from these two, you need to break down into another formulations, which we are going to find the stress and the strain. Okay. So the displacement, you have the original size, right? And you have the displacement that is after the testing or when they change for a little bit, right? So this testing is done by assumptions is they are going to take this as slow as possible. So the rate should be slow. Why? Because we would want to make the specimen displacement is going to be as small as possible every rate of time. So every time it takes some pulling, it needed to be really slow. Okay. And after we get this, then what we are going to do is, so of course this is the fourth specimen, and then the final specimen, it should be broken into two. It should be broken into two. So we test this specimen until it is failure. Okay. So after we get, usually the final result after some time is this graph, the stress strain graph. and you will have all this mechanical property, which I will go into review. I think you have learned this before, but I'm going to review what is this and what is the importance in our chapter. So the first thing you need to do is you are going to take the displacement and the forces into the stress and strain. So forces, or P in here, you are going to define with the original section, cross-section of the specimen, which is standard in the ASTM, the material standards. You will get the original surface area, and you get the stress, okay? And then for the strain, you get so you will get the data looks like this. So if you are familiar with Excels, so this is what you get, okay? I should show you the real data, but I need to look for one. So this is usually we have D, and we have F, and then this is some number, okay? And then one by one, you are going to get this sigma and the strain. Okay. So sigma, you get the F defined by the original cross sections, and you need to define all here with the same. So assumptions. Okay, this is important. Assumptions here for every stress you compute. The area is going to be the original size, right? But we are going to see there will be a problem. Okay? And then the strain, every part that is going to be changes. Okay? So maybe this is one maybe really small, maybe 0.01 millimeter. Okay? So we go take that delta divided by the original cross section, and we get how much it's going to displace, right? And then for every length, we are going to have a new strain, right? We have a new strain, we have a new stress, because in every period of time, of course, the forces will be different. And this is what we expect. So when we take our time to pulling the steel, we get this line which is expected until some part on this C, okay, which it is not going to be straight line. It is a little bit bent here, and then a little bit getting a horizontal line. Okay. Usually here this is really smooth, but if you read or you work with the data, it is actually looks like this. Here, and then you have like a little bit noise here, and then like that. That is just to show you that this is when the steel or the specimen is no longer elastic. Okay, so what's the deal with the elastic? So every time you see a straight line on the mechanical property or mechanical curve stress strain, this straight line, it gives you the idea that this is a linear equation, right? So what's happened when the linear equation happens? So it happens that when we have this, the modulus of elastic, or Young's modulus. Okay? This is when this elastic region. So this is when we get the E. Okay. Or here is the E. Okay. So let me write here that this is when the E happens. Modulus of elastic, or Young modulus. Okay. Okay, now what is modulus of elastic? Of course, if you see the graph, you see, oh, the modulus of elastic is when the stress and strain serves in elastic region, or they have linear equation between those two. Of course, that is the definition. But what is the importance? What is the importance? What you know of the E? What if materials has high value of E? What does that mean? Okay, if you learn material science, you should know. Okay. What's the significance? Okay. If you have high value of E, what happens? Okay, now let me get this straight. Okay, so elastic. What is elastic? I didn't bring any material now. I should bring something to demonstrate. But imagine, like you have a, I think you know, like a ruler that is metal ruler. You have seen. If you put straight and you play with that, you pull it with some forces and you release. Is it going to be bent or back to straight? Hi. You have a metal ruler. You have seen one, right? What happens if you bend and you release? Is it going to be bent? Huh? Is it going to be bent? Have you seen one? You play, it's a small force and you release. Going to be straight again, right? Okay, if you bend, it's bad material. People buy the metal because it's good, right? It has a good structure. So that is elastic. Okay, did you get that point? Elastic. Why does it going to be linear like this? Because when we take and then we pull off, so when we pull and then we release, it's going to be back into the original position. Okay? So that's what it is. So when you have high E, it means that it has high, let's say, rigidity. Okay, that's the English word, but I'm not sure what else could be describing. So let me write here, high E, high, or maybe let me just write rigid. Okay, let me write rigid, and you can look the dictionary. What is the best way to describe? Okay, rigid or rigidity, or I would like to say brittle, but brittle is not a good word, because brittle maybe you're thinking on ceramic that is easily to break. So let's say rigid. So it's going to be difficult to bend. Okay, difficult to bend. Okay, now after elastic region, you see here, this is the word yielding. What is yielding means here? So it is going to take some time. So the material will have some retention. It will have some retention to. Okay, so don't make my original form going to change. Okay, so it is still in that position until some point, which we call this point here. This is the strain hardening. Okay, this is, I think, a little bit technical. I will explain what this strain hardening. But overall, from this point here, a long way until it is failure, we call this is a plastic behavior. Plastic, not in a polymer definition, but plastic in a sense that they are going to be shaped like a clay, okay, like a play or a child's play, like that. Okay, that's plastic. Okay, so it's plastic behavior, and then we have a strain hardening. What is strain hardening? It's a little bit difficult to explain, but I would like to know if you have heard before. Have you heard before? Strain hardening? You have heard before? Okay. Okay, it's hardening when it is getting a displacement or strain. But why does it happen, or what is the significance? Anyone want to explain a little bit? It's a little bit technical, but since we are in the tensile testing in steel, the strain hardening is related to what we call the dislocation movement. Have you heard dislocation? Okay. So this is, let me just write off really quick. So this is what we have here. There will be what we call dislocation movement. And when the dislocation moves, so dislocation is, so every material is not perfect, right? There will be, so if you look at the crystal, the material, there will be some point or some spaces that is, we call the defect, right? In metals, we call this defect, there are several ways. There are dislocations, and like a point like this, or there are dislocation like a line, and there are several others. But what does it mean is when we move the material, or when we pull the material, we give forces. Imagine all the atoms, all the crystals is going to take the same force. Remember, we have learned that the forces is distributed along the materials, right? What happens when we have the defect is the defect also moves. Okay? So when the defect is moving, it is actually start to have this plastic behavior. And at the same time, the movement of the dislocations will make the whole system become hardened. Because it is like, you see, like, I should give you some video, but later I will give you some video about that so that you can have the visuals. So it's like an obstacle. So when you pull something, but there's someone is, it's stopping you. So that's why it's hardened. Okay. So the defect is moving, and at some point it is harder. But at the same point also, after some time, that part of the defect will be the part of the failure. Okay, so it's like someone stopping you, but somehow when you pull with a greater force, it's pull away its brakes. So that's when it is failure. Okay, so it is going to be related to this dislocation movement that this all happened, and the plastic behavior happened in steel. So and at the plastic behavior, we also have what we call the necking. What is the necking? Anyone remember? Yeah. Anyone want to explain what is necking? He gives a clue, like a small, like a. So the tip. Yeah. Oh, the tip. The edge of the material. The edge or the center? No, center, right? Okay. But that's correct. So the idea of the necking is actually. So imagine that we have the material looks like this, right? Okay, imagine materials look like this. Let me just zoom in first. So after some time, you pull this out, right? So let me just pull this going on top. This is going to be here. And then it's become smaller, right? Well, it's too long for scale, but let's just imagine that this happened, just to give you a good image. So this is what we call a necking. So the necking means there are changes in the area. Which area? The cross sections. Okay. So this is a problem. And this is a problem when you deal with the original formula here. So in calculating stresses here, all the numbers here are we get from this. But when the next necking happens after the strain hardening, which is in plastic deformations, then the stress is not the same because of the necking, because the area now is changed. Every time the area will be changes. So we need to make another curve, okay, which simulates this, the true stress and the true strain on that plastic behavior. So we call that the true stress, the true strain. Okay. We can write using this, or we can write using the surface area or the cross section. So we have now the true stress and the true strain. But the previous models still works for design. Okay, at some point it still works for design because we are not going to take all graph itself. But this is if we want to know the true, then we are going to need this area that is changes during necking. Okay. Now let me zoom out a little bit. So what is important here is, I forgot to give you the idea here. So the yielding here, we call also this is a perfect plastic behavior. Okay, and you see that we have some important stresses here. Okay, so this is we call the proportional limit. So this is proportional, or let me just write proportional. We usually use this proportional stress for approximate the offset, okay, the offset yield stress. This one we call the yield stress. It's the first time that the material is going to be plastically deformed. And then the stress F, this is the ultimate stress. Or the sigma U. And G here, this is the failure. Okay, this is failure. Okay, now look at the graph that we still using this red curve. We call this red curve engineering stress strain. Okay? Engineering stress strain. C and D is a yield stress, both of them. So C and D, they are yield stress. We call lower yield or upper yield, depends on their positions. Okay, now the proportional limit is based on some percentage of the let me write here, proportional is going to be 0.2% offset. Okay, now from the basis of the steel, it is perfectly giving us a lot of data and a lot of mechanical properties. Okay, so we get the E, we get the yield stress, we get the ultimate stress, we get we call this whole area, we calculate with integrations. That is what we call the ductility, the toughness. So toughness is the energy under the curve. Okay, and then since we know the yield stress is around here, we estimate that this is, if we take the proportional line according to this straight line, we get this is around 0.2%. And this is a good way to approximate some materials that is maybe still in metal material or metal alloys, which not every material have this. In steel, we can see clearly the yield stress, okay? But in other materials, that is quite easy to deform, like aluminum. The aluminum will have a smooth line, so they don't have any noises here. So we cannot really see the differences between the yield stress and, so the point in yield stress is like we don't really know. So how to assume or how to approximate is we take 0.2% offset from the point, and we take the line parallel to the linear equation for this one. Okay. And then we get the point, oh, here, that's the yield stress. So that's how we get it. Oh, this, let me write with the yellow. So this is the offset. Okay. Or let me write here, the A to B is elastic, which we get, or maybe let me write here on the left, which we get the E when the sigma is still below the proportional limit. The unit usually in GPa, gigapascal. And then from B to C, we are going to have a yielding. So yielding means small increments or small changes of load required to a given elongation. So the stress or the forces needed on this yielding is very small. And when this happens, as stress increase, I will write here, grain boundary start to move. Or slip, okay? Not just move, but slip. So when it slip, it is moving really fast. And B to C and to E. B to C, to D, and then to E. Okay, the whole thing here. And then E to F is strain hardening. I will just write, this is dislocation movement at peak. Okay, I will write at peak. I hope you understand what I mean. And then F to G is necking. Necking until failure. Okay, I will make another summary, okay, from these descriptions, what we get from all the definitions here. Let me write here. I forgot to write. The whole thing here, when the grain boundary slip, is plastic deformation. This is also the same for the dislocation movement. Also plastic deformation, but the hardening part is because of the dislocation. It's moved until the very end, when they become the huge obstacle of the materials. So it will make the material in higher stresses when they pull away, and at the end they will have a failure. Okay, but I hope you can understand all of this, not because you read or you memorize everything, but I hope you understand from the phenomenon. What happened when you read the graph, you know, oh, what this is exactly what happened. And you know how to get the idea from the strain, stress, what properties you get, and then how you can summarize every property. So let me summarize a little bit here. So, and while we are trying to summarize, this is another example, and this is, I think they are using different unit. This is using the KSI, the British and somehow the American units. So we have this is carbon steel. Okay, I think we can adjust the previous graph as a carbon steel. This is really similar. And then the other part is the other alloys. And this is other alloys. Let me check which alloys is that. Yeah, this is the aluminum. And then this is the alloy for steels. They are high alloy, low, and then the plain carbon steel. And this is for some aluminum with different alloys, different alloying elements. So if you see the differences, and this is what I talked before. Okay, in here we see the yield stress easily. Okay, in the steels we see this yielding easily. But if you see in aluminum, if you see the difference, it's really smooth. They are nothing similar to these steels. Okay, so that's why we need this. Okay, this is. I hope when I give you this example in the questions, you know how to do it. Okay, so basically what you need to do, you take 0.2% offset from this graph. It means that 0.002. Okay, so this part, okay, you take a line. So you need to take ruler. You make a line, and then this point become your yield. Okay, yield stress. Okay, this point become your yield stress. Okay, so that's how. Okay, this is especially for aluminum case. Okay, for aluminum, you cannot really see the yield point. The yield point. So this is how you assume or how you predict the yield point. Okay, now for design properties, what properties should we take notes? Okay, so there are several significant properties. For the first one, the easy one that can be described is strength, right? Let me write strength. So what kind of strength we have? We have the yield, or this is the sigma y usually, and then the ultimate strength, and then the stress at failure. The definition for the yield strength is that this is strength required to make a material starting to have a plastic deformation. So you can also define the yield strength as, so because it is starting to have plastic deformation, you could say the yield point is the highest stress, okay? Or let me write here another point of view, or the highest stress material can hold before before yielding. Yielding, sometimes if you learn from some movie or films, yielding means give up. Yield. Especially for classical movie or from TV. Okay, yield strength, and then ultimate strength. And then I think ultimate strength easy to describe. It is the highest or the maximum value of stress. So maximum value of stress that material can hold. And for the yield and the ultimate, the point can be seen from the curve directly, right? Okay. or you can see from the data for the ultimate. And the stress at failure is basically the point at a failure. You need to know the differences. Okay, the stress at failure doesn't mean that the stress used for material and then material is going to fail. It's not the same. If you see the graph, this is not the highest, right? The highest one is the ultimate strength, but the stress at failure means the value of stress itself when the material is failing. That is the definition. Okay, the second property. So first is strength, the second is stiffness. I think this is better way. Or rigidity. So we can say the material is rigid or stiff or not. We can see from the modulus. Okay. So this is going to be ratio between stress and strain at elastic region, which we can simply rewrite this as E, or Young's modulus. Okay. Now the third one we call ductility. So as I mentioned, this is going to be the area of the under the curve of the stress strain curve, right? But this is going to be defined as materials that can undergo large strain before fracture or failure. Now, if you have a large strain before fracture or large area under the curve, we call that is a ductile materials. Which means we can also say that they can store a lot of energy. Because basically, you have force, you have an area, you get the Newton over meter squared or the pressure. And if you integrate that, what will happen is you get something that is related to energy. That is why we could see the area itself like a storage for energy. So when we stretch something, or maybe stretch the steels, actually we stored some energy proportional to the way it's displaced or the way it is having a large strain. Okay, so I hope you get that. Okay. So when we have that, we call the materials is ductile. If the displacement or the strain is small, it means that they can only store lower energy, which we call the brittle material. Okay. So the opposite of ductile is brittle. So ductile and brittle. And brittle and ductile, it also refers to, they both refers to modes of fracture. Okay, mode of fracture. Okay, do you want to have a break? I think we can have a break. Okay. Okay, let's go back. And this is just an additional information that sometimes in a graph, we could make this two scale of graph. So this is the elastic region here. We zoom in and we get this. This is the elastic region, and you see the two numbers here. So this is going to be the number for the actual graph and the number for the elastic one. Okay, so we have to tune, and then all the points, they have the same structures. Okay. This is usually, we use this to get the a good visualization for the line, okay, for the E. In the actual graph, sometimes the lines must look like this, and maybe it's not really a good way to represent the E. So sometimes we have this graph here that is a different scale for the elastic region. Okay. Okay, now let's go to some part of the ductility that I want to get into. So basically, what we have here, this is an example. The picture here is the example for a typical fracture. Okay, so this is we call this type of fracture here, we call the cup cone fracture. Here is cup cone fracture. So this is from specimen from the hot rolled specimen. And some of the ductile material, if you see, if you compare with the brittle material, the difference is that the ductile, the area under the curve has a large area. For the brittle, it's very small. Okay. And this is a typical for brittle material here. It has a different mode. If you have a chalk, okay. If you have a chalk, so let me write here, if you have a chalk, which is very brittle, right? So please find a chalk. Okay, I think from other classes they have a chalk. Find a chalk, okay, and then what you need to do, okay, you need to find two chalks. The first chalk, try pulling with the axial forces like this. So let me describe this here. Okay, so the first case, this is a chalk, okay, a chalk, and then pull from two different sides with your hand, okay, pull. Okay. The second chalk, so find two. So the second chalk is twist, try to twist. Twist, okay? Twist. So this is, so first is you take tension. The second is twist. The result, what will happen with the chop, it will be really interesting. And let's do that. Okay, let's do that. Just find chop somewhere, and I hope you can take photo or video. Okay? And please show me maybe next week. Okay. So this will be very interesting. So this is going to be some property for brittle material. So that is, I think, for chop. So this is a typical from a brittle material, something like this. We expect something like this, but you will see the difference, number one and number two, if you try to do with your own. Okay. And then this is another example. If we have a superplastic material, we could have like this much strain, which means that there are a lot of energy stored inside, right? And it is going to be 1000% elongations. So the percent elongations, that is going to define the ductility of the material. So let me give you an idea here. So the percent elongation this will be equal to the length, the final length minus the original length divide original length multiplied with 100%. This is let's say fracture length. This is original length, or we say the length for the gauge length. Okay. The second, aside from the percentage for the area, is the reduction of area, or area reductions. So the percentage area reduction is the original size minus the fracture area divided with the original. And I think both of these are quite intuitive if you imagine how the material can be stretched. So this is original. This is final cross section at fracture. So suppose we have this original size. So we have the L, we have the area, right? And if we stretch the area, supposed to be reduced, have a reduction, and the L have a extension, right? Extended. So I think it's quite easy to see how this works for compute the ductility. Aside from the energy, using energy, so we can use the elongations and the area reductions. Okay, now some notes on the elastic and plastic we could see from this graph. So we call this is another size, or another important size. We call also sometimes this elastic limit. Okay, so for the yield, we can also say this is an elastic limit. So whenever the stress is before reaching this limit, if we release, the material still the same. Okay. it will be going back to the original form, okay, with the same geometry. So that's when we have in the elastic behavior. But when we cross this, then if we take an offset line, this is how much the material will be permanently deformed. Okay, this will be after some deformation here. So the rest will be how much is recovered. So some part of the material will be deformed permanent, but some parts still can be going elastic. Okay, so it still can do some elastic. We call it elastic recovery. So we can still have some recovery. So before the elastic limit, so let me write here. So before the stress at elastic limit, material can go back to original shape. Okay. But if you cross this, okay, so if sigma is greater than elastic limit, let's say from C to D, then it follows this offset line which define the permanent set. So this is going to be permanent set that's plastic, has been plastically deformed. Or we could also call this a residual strain. Okay, strain that is going to be a residue. So it's not going back to the original. There are some models, I think I have them right here, so let me just draw, that we call the perfect elastic and perfect plastic. Let me just draw here. So let's say this is going to be that. Sorry, should be this line. So this is sigma yield. This is the strain yield. So we call this linearly elastic, and this is going to be perfect plastic. And somehow this models, although it's not the real model, this is not the real model, but it is a good model for showing you how the stress in mechanics of materials or torsion it can work, because we simplify the models and we use this linearly elastic, especially for the, after this we are going to see the Hooke's law, just to get the idea, okay, how it looks like for design property. So we are going to see this way. So this will be used for describe inelastic behavior. usually in axial deformation, in torsion, okay, or in bending. At least for our course, we are going to cover the axial deformation and torsion. Okay, we are going to cover those two. For bending, I'm not sure. If we have time, we can, but if not, then maybe only axial deformation and torsion. Okay, there are other deformation which we call creep, but I think I will, maybe if we are having another chapter that has this problem, we are going back to this behavior, but I think I will just skip that. And all I mentioned before, they are primary property that is we can get from a standard carbon steel stress strain curve. Okay, let me continue to the linear elasticity, or the Hooke's law. We are going to connect this to I think the Poisson ratio. So the Hooke's law is basically works in the elastic region, right? So elastic region is when we have the sigma over the strain is equal with E, and E becomes our standard. Now in terms in this specimen, our sigma and strain, they are on the x-axis, right? So we could write, or now we could write here that the stress at x-axis equal E multiplied with the strain axis. Okay, now this is what we call the Hooke's law. This is, maybe, let me write this strain with more curve here. Okay. Now this is the Hooke's law. And usually we are using the Hooke's law for spring. For spring, we take some forces, some stresses, and then we release, and then it's going back to the original shape of the spring. Okay. So suppose that we have this specimen, and to simplify our mechanics, we say that this will be homogeneous. Okay, so no problem with the material, so all the same. And then we could also say it's isotropic. What is isotropic? We have anisotropic, we have tropic, isotropic. But what is that? What does it significantly mean? It is related to how the materials can have different crystal structure, right? And sometimes, how to, do you know how to cut diamond? Yeah, but how? I mean, the techniques, not the materials with to cut diamond. You cut diamond through. Yeah, through which part of diamond that we cut usually. There are some part of diamond that has some weaknesses. You can look for, I think, some googling some part of the website. I think there are some weaknesses, and in general, materials have different crystal structures and different orientation of the structure. That's what we call isotropic or anisotropic. Okay? So if we say it's isotropic, it means that it doesn't have different orientations. So if we have different orientation, it means that somehow, maybe, like if you, well, this is in another course in polymer. If you have armor, Kevlar is made from the fibers we call aramids. Aramids is having a unique structure that, so imagine that this is a fiber. They are weak in the sides, but they are quite strong if we stretch this fiber, they are quite strong. So the way we fabricate the Kevlar is we put this here. So this will be like a needle. So when the bullets shoot, it can deflect with the bullets because it has a strong, it has a high strength in this direction for the fiber. Okay, so that's what we call the crystalline has a different directions, and sometimes in one direction they have a stronger property than the other directions. Okay? But for our course, we are going to simplify some. I think for most of the parts, we are going to say that the material will be homogeneous, will be isotropic. So it doesn't matter you pull in another directions, they will have similar reactions. Okay? So for example, if you stress this, maybe in the real world, these have a different crystalline, and maybe they have some weakness, and maybe it has some fracture that we are not anticipated, right? But in our design, to make it easier for mechanics calculation, this will be simplified, and we say, okay, it's all homogeneous, maybe it's steel or it's another material, and then it's isotropic. So we don't really care different crystal orientation. We don't really care about that. Okay. Okay, so this will be valid. I mean, right here, the Hooke's law valid for uniaxial tension, which in the picture here, uniaxial tension, or compression. Compression also works the same thing with the tensile within a linear properties. Okay, I think that's the goal. And then what else? Aside from the Hooke's law, I forgot to write here, we are going to have what we call the Poisson, not Poisson, Poisson's ratio. Let me check, do I have the, oh, I didn't have. So Poisson ratio is basically the difference, okay, or the ratio. Okay, let me write here. The Poisson is basically we have a strain on the transversal direction, which is the vertical one, and then let me just write first here the strain in longitudinal. Okay. So we can write here as the Poisson ratio is equal minus the E, or the strain transversal, divided by the strain. I will just write longit like that, longit or longitudinal. Let me just write completely. Okay. And Poisson ratio is good to know how much we have, like whether the material tends to go really long, or maybe tends to go maybe not so much from the original shape. So when we stretch the material, we are going to see that it's going to be, for example, this part of material is going to be longer in x directions, right? But in z directions, it's going to be smaller. Okay, so that's why in Poisson ratio we need to multiply with the negative. Okay, because some of part of the strain will be a negative. So we need to multiply with negative to make a positive. Okay. Okay. That's the stress strain. Let me check. Well, I think for some part of our course, we are going to have some example here. So here's the example, but I think I forgot to change the units. So I'm using the other books that has the like American Standards unit, the KIPS, feet, inch, KSI. So usually KIPS is equivalent with Newton. There are some conversion for the number, but let's say we are just going to use this. Okay, so feet for the length and inch. So we are going to, I think, convert between inch and feet, and then the megapascal is equivalent with the KSI, or kilo squared inch, kilo squared per inch. And then we have E, and we have the Poisson ratio in the picture. Okay, so we need to calculate the delta L and the delta D. So we have the delta L here, which is elongations, and then D. So we have the original shape and the reduction area, So we are going to calculate that. So what we need to do first, we need to determine, so first, need to determine what? Okay, now we see the delta L here, and we see the difference in the delta D, okay? But how do we know if the material is going to be, like, if we can use Hooke's law or not? It doesn't mention if we can or not. So we need to make sure and prove whether this is going to be applicable, okay? Whether the Hooke's law applicable or not. How do we make sure is, we are going to see, because it has a sigma yield, 50 KSI. So we need to find the stress that is happening now here. Is it going to exceed this 50 or not? If not, then we can use linear elastic, okay, assumption. Okay, so that's what is going to happen. So we need to determine the stress. Okay. If stress is less equal the yield, then Hooke's law applicable. Oh, let me just write here, move a little bit, oh sorry. Okay, so Hooke's law applicable. Now, I think this is quite a simple forces for the diagram forces, right? So it's just, I think we can make this a very simple diagram. And we say this is just the P, this is the P, right? Or let's say we take this as a, let's say this is from the middle part. Okay, let's say we cut the rod, we cut the rod, and based on this, we might have here a reaction force, which we could just call this a function or a force, okay, just F. And we say that the sigma of F is equal to 0, which means that we are just going to have the F as P, or a constant. So then, because we only have this P, then the sigma in x-axis, because this is the only axis that works with this rod, we could find by taking this P over A, and this P is 10 kips, kilopounds, and then divide by the area. Since the diameter is diameter is 1 inch, so the radius is 0.5. So we can take the 0.5 inch squared. So if we count, and I think I will trust the numbers here, but you could check. 10 divided by 0.25 multiplied by pi. This is around 12.7 KSI, which is, this is going to be smaller than the sigma yield, which is 50 KSI, right? So linearly elastic behaviors occurs. So let me write here that linear elastic behavior occurs, okay? And now, since we have the E, the modulus, okay, remember the modulus is the stress divided by the strain, okay? Or in our cases, in the x-axis, so we can derive, or we can write the strain in x as sigma divided by E, or we could get the sigma in terms of P over AE. That's for the strain in x-axis. And then from the Poisson ratio, we could assume the transversal strain as a radial strain here, because this is a rod that is like a cylinder. So we can just imagine that this is like a transversal here, and this is the longitudinal, okay, the horizontal one. And then we can use the Poisson ratio, which is 0.3. Let me just write first the strain. So the strain for the radial equal the Poisson ratio, or maybe negative Poisson ratio, and the strain in x-axis, or the longitudinal. So we could write here this Poisson ratio multiply with the strain x, which I write before, so P A E, okay? So we get the strain radial. And then we get the displacement for the delta L. This is we get from, or if you want to write the complete works, we can write from the strain. We can also write as delta L over L, right? Or we could write the delta L as the strain in X multiplied with L. And in the delta D, we could also work with the strain radial is the delta D over D. We need the strain in the vertical, okay? And we can write here the delta D as strain radial multiplied by d. And we get, just put all the numbers, okay? So we get, here is the the E strain XL. This is, we are going to have PLAE, okay? From here, PAE, PLAE. This formula we are going to see a lot in the next, I think next chapter. We are going to see a lot. This is related to the axial deformation. Okay, PLA, play. Okay, it's easy to follow. So we just put the numbers. I think you could just count in all the numbers inside. And then the radial, we could get this from the Poisson. So negative Poisson ratio, P, A, E, and D. Okay, and then you get the number from here. Okay, I think I will leave the numbers to you. Okay. And I think for some of the examples that might come, as usual, that will be for every Tuesday class. We are going to have exercises, okay? And I think, what is the date? Now is March 4. Let me check. So I think next 2 weeks will be quiz, okay? Quiz chapter 1, chapter 2 around. Okay. So the quiz will be on the Tuesday class. Okay, so I think it will be 19. Okay, so I think 19. This will be quiz 1. So topic is statics and stress strain. So only 1 hour class. Okay. Maybe I only prepare 2 questions only. Okay, and bring calculator, and I think I will make this open note. Okay. So you could prepare A4, okay, A4 note. Okay. Okay, the last 10 minutes, I will just want to introduce you to another type of stress, okay? So what we have before is, we call the normal stress, okay? The extensional stress or the axial stress. The next part of the stress is, we call it is this shear stress, shear strain. And we are going to see how they are going to works. I forgot to put here, so this is the definition first. So by definition, okay, if you see what is the shear, so if you could imagine, like perhaps usually I bring some parts of component, I mean from toys, to see what the shear could look like. But usually, if you have some toys that are easy to plastically deform or elastic, you can see if we shear on some point, we are going to see that some side of the materials will feel that they are getting some forces going through this direction. Okay? And in every part of the materials, they are going to have the same or having the distributed shear stress. Just like this axial stress, they have the distributions. The material also have the distributions. And for each element, since we are talking on small elements, then it is going to be intuitively clear that we are going to need this limit. Okay? Just to assume that they are going to have the small element that have small distribution of the force or the shear, okay, shear strength or shear force. Okay, so we could describe this with the delta V or the shear force defined with the delta A, the cross sections. Okay. So it's quite similar to what we have in the as in the axial stress, which we have the normal force defined by the area, but now we have the shear force. Okay, so this is the shear force. And this is the shear stress. And usually we say the shear stress, as the symbol say, is tau. Okay, tau. And then from the limit, we get the idea on differential and integration of the shear. So we could write as an integrations of tau dA according to the endpoints along the area A. Okay? And then, similar to what we have in the normal force and normal stress or axial stress, we can also get the average. It means that all the forces here, or the shear force acting on area A. But more applicable or more practical is what we call the direct shear, which we can see from some of appliance in our daily life applications, such as the shear in bolts or pins or rivets or in the welds. So this is some of example, okay, for we call the direct shear. For example, here for the pliers, when we put the force here in the pin, we are going to see that in each element they are going to have some shear. Okay. Also here in the metal punch for paper, if you pull some forces and if you punch and then you see that it is going to slide inside, right? It's going to slide. Now the slide here is also has the same, like it has the shear. Okay, so this is what we call the direct shear. And the significance for the shear is when we have the diagram like this, like a bar, and then we have some point of it have a direct shear, then we need to calculate that as our shear. Okay? And there will be two different shear for the direct shear. There will be a single shear and double shear. But I think that will be next week. Okay? So I think I will just end up until here. So let me